In this video, we will solve combined loading problems. The first problem, we have a rectangular block and it is subjected to a force 40 kilonewton at its corner. So the question is determine this normal stress distribution acting on the section through A, B, C, D, and the weight will be neglected. So this 40 kilonewton on the corner will cause internal forces and moments in section A, B, C, D. Since it is not applied in the centroid, it will cause a compression, and bending moments around Y and around the X-axis. How do we calculate? Let's calculate mx. So this is my x-axis. Well, the moment arm is this distance, 0.2 times 40 kilonewton will give you 8. As you see, 8 kilonewton meter around the x-axis. Next, we have the y-axis. If you take the y-axis, this distance is 0.4. 0.4 times 40 will give you around the y-axis 16 kilonewton meters. So we have on the section A, B, C, D a normal force, a bending around X, and the bending around Y. Let's calculate the stress distribution due to these internal loads one by one. First, the normal force, minus 40 compression divided by the area gives you minus 125. Next, the bending moments, the first one, the mx. My x-axis is this one. As you see, on the x-axis, which is the neutral axis, the stress is 0, and since the bending is in this direction, we will have on the front wall a negative compression, and on the rear wall we will have a positive tension. So the maximum values of these on the surfaces are 8 kilonewton times the distance from the neutral axis, 0.2, divided by the moment of inertia, Ix, will give you 375. Bending is around the y, that is my my. The distance is 0.4, and as you see, the application of a bending in this direction will give you negative on this side, positive on this side. So we have the stress distribution due to these forces and moments. What we have to do is make a superposition. Well, this is due to n, that is due to mx, that one is due to my, or the other way around. So take the point A, minus 121, plus 375, plus 375, that gives you 625. Let's take another point. Let's take C. In C, I have again a negative. You see the distribution of the normal stress due to the normal force or axial force is uniform. So again, in C, I have minus 121, 25. Here I have minus, as you see. Here I have again a minus, and the total is minus 875. You can do the calculation in a similar way for B and D, and your stress distribution can be shown graphically this way. So these, and where's the other one? This value, they are all negative. Only in point A, I have a positive tensile stress. Next problem, a solid rod. Well, external forces are applied. So the critical section is here. Well, point A is the point where we have to calculate the state of stress. First, I cut in this section and I write down all possible forces and moment. So the forces are Ny, Nz. I can add also Nx. Okay, these are the forces, and the moments are My, Mx, and Mz. So the next step is, so let's try to find the internal forces and the moments one by one. Well, it's not shown here, but we can also imagine that there is also an X. But since the external forces do not have any components in the X direction, and X must be 0. So we can just forget it and come Ny. Ny, and that 500 are the two forces in this direction. So Ny should be 500. Well, if you think the same for the Z direction, you see we have 800 and NZ, so NZ must be 800 newtons. You see, you can do the same, well, by writing sigma Fz equal to 0, and that is NZ minus 800 equal to 0, and NZ equals to 800 newtons. So, but we are just doing it in a direct way. We do not write the equations and just calculate the results for My. My is a moment around the axis of the section, which is actually a torsion, and the torsion created in the Y around the Y-axis is in equilibrium with the torsion created by this 800 times this moment arm. So 800 times 14 centimeters is the torque My. You see, this force is parallel to the Y direction, so it does not create any torque at all. So that was My, and now when we come to Mx, this is the bending of this section around the X direction, well, which is Mx should be equal to the moment created by these 800 times 10. So 800 times 10 centimeter gives you your Mx value. Well, what about Mz? This is your axis now. Well, your Mz is in this direction, trying to rotate the section around this axis. So the external load, which has Also, a similar effect is 500 times, as you see, this moment arm, which also tries to rotate the section in the around the Z. You see that 500 times 14 is your mz value. Now we have everything. You see a normal force, a shear force. Your normal force is 500. Your shear force is 800. You have two bendings and one torsion. So the next step for combined loading analysis is to calculate the stress distribution for these section loads and moments one by one. Let's start with the normal force. Forget these. Well, we have a normal force 500, which is positive. 500 divided by the area gives you a positive normal stress component. Next, we come to shear. We have a shear, as you see. Well, the shear force is 800 newtons in this direction. And as you see, we know that the stress distribution due to this shear force can be shown like this. On upper and lower ends, the stress is zero. On the neutral axis over here, the shear stress is maximum. Okay, and my point A lies on this axis, so it has a maximum shear stress. Well, the formula to calculate the shear stress is like this. You have the shear force, you have the moment of inertia around the axis, and the thickness, which is this thickness, this is the diameter, and you have the Q value. What is the Q value? The Q value you calculate by taking this area. Well, if this is your area A prime, and the centroid of this area, the distance of the centroid from the neutral axis is y bar prime. So this you can find in geometry books, and you get your Q value. And this value you can put over here and find the tau max in point A. Well, in our other slides, we used also a much simpler formula. If you have a simple section and you have a shear force for a circular section, the maximum is tau max equals to 4 over 3 V divided by A. So you can use also the simple formula only for a circular section, and the result will be the same. You also remember that for a rectangular section, distribution is similar, and this maximum value is tau max 1.5 V over A. So if you have simple section, you prefer not to use this formula, but instead you can use these simple relations. Now we have finished the normal force and the shear force. And finally, torsion. We have a torsion 11,200 Newton centimeter. Well, it will develop on the surfaces a maximum shear force of 1120 times the radius divided by the polar moment of inertia, 169. And my point A is on the surface, So the torsion creates a shear stress of 169 in point A. Now we have everything. The stress distributions due to these 5 different loads. So I need to make a superposition and find the stress state in point A. I know that the normal force and the bending moments are creating sigma. That means normal stresses. That means 283 plus 211, this is 0, will give a sigma of 214. And we also know that the shear force and torsion will create shear stresses, and this is why 604 plus 169 will give a torsion of 175. So this is the stress state in point A. Well, a last problem. There is a clamp, and this clamp is made of 2 members. So this is the member 1, and the second one is this one. And these are pinned over here. Okay. In point A, they are pin connected. Well, in C and B, which are the clamping surfaces, well, the compression is 180 newtons. And in order to apply this compression, there is a screw. And along the screw, only tensile forces act along its axis. So the question is, well, this is your section AA, and determine the compressive stress in this section. Well, the first thing we have to do is take one part, and we have to calculate the forces in pin A. So if you take this part and draw the free body diagram, and you see, well, this is my external force. This is not known. And the unknowns are the force on the screw and the X and Y components of the force in A. So if you write down the equilibriums, or you can only make sigma MA equal to 0, the moment around point A, you find that F times 30, F times 30 minus 180 times 70 times 70 must be equal to 0. So F is equal to 180 times 70 divided by 30. That will give 420. So you can easily find that the force acting in the screw is 420 newtons. And now we're looking for the stresses in section AA. We take again this part. Well, if you take this part, it will look like this, okay? So the external loads are here 180, here you have 420, of course, Newton. So you're looking for the forces and the moments in this section. Okay, you don't know these values. If you write down the equilibriums, you find that M is 0 and the actual force is 240 compression. So, as seen, The only force acting in this section is compression. Take this force divided by the area, and you find the compressive stress in the clamp section AA. Okay, in this video we solved 3 combined loading problems and showed how the stress analysis for certain points are made. Thank you for listening.